Okay, so now we have a couple examples, right? Let's go ahead and look at this molecule right here. We have a hydrocarbon, 1, 2, 3, 4, 5 carbons. Therefore, we know this is a pentane molecule, right? And right next to it, we have neopentane, right? Now, we understand that pentane here looks very different than neopentane, its counterpart, right? But what we see is we have 5 carbons. Now let's go ahead and add in those hydrogens, those implicit hydrogens, and see how many of those hydrogens we have. We have 3 hydrogens here, 3 hydrogens here, 2 hydrogens here, 2, 2, and 3, right? Therefore, we have a total of 6, 10, 12 hydrogens. So this is going to be C5H12. Now, a little tip to learning how to quickly count how many hydrogens you have in a hydrocarbon is that, remember, the formula for hydrocarbons or alkane is going to be CnH2n plus 2. All right, so we have 5 carbons. Therefore, that would be C5 and then 2N. So 2 times 5, 10 plus 2, 12. Right? Now let's go over here to neopentane. We have 3, 3, 3, and 3 hydrogens, implicit hydrogens on each of the endpoints. And how many carbons do we have? 1, 2, 3, 4, 5. Therefore, the molecular formula is also C5H12. Now, from our definitions, we know that this means that these molecules are therefore going to be constitutional isomers. Why? Because they have the same molecular formula, but different connectivity. How the atoms in this molecule of pentane are connected completely differs from its counterpart, neopentane, but they both have that same molecular formula. Therefore, these are constitutional isomers, right? Now, let's go ahead and take a look at these molecules, right? Clearly, we see that we have 1 carbon in the middle, in the center, and then we have an alcohol, a fluorine, an ethyl group, and a hydrogen. Here we also have an alcohol, a fluorine, an ethyl group, and a hydrogen. Therefore, these molecules actually have the same connectivity, right? These molecules, while they have the same molecular formula, they also have the same connectivity. Therefore, these molecules cannot, I repeat, these molecules cannot be constitutional isomers. Therefore, they have to be stereoisomers. Now, remembering that we have 2 main types of stereoisomers between enantiomers and diastereomers, we have to then find a way to differentiate whether or not these molecules are going to be enantiomers or diastereomers, right? The easiest way, before we talk about the way that I prefer to do it, one way that others do it is bond rotation, which is basically taking one of the molecules and rotating the bonds around until you get to see if you can superimpose this molecule on the counterpart that you're comparing it to. Now, as you can see, sometimes you're going to get structures that are extremely complex and you're not going to be able to superimpose via bond rotation. Therefore, using this method will help you, especially as it does give you clarity on definitions such as chirality and also getting you into optical activity via RNS. Right? So first, how do we tackle a problem like this? First step is check the connection, right? We have to check to make sure that the atoms in the molecule are connected the same. If they are not connected the same, then we have 2 choices. They can either be constitutional isomers or they can be different compounds, right? If things are connected differently, those are the only 2 options. Constitutional isomers, meaning they have the same molecular formula, or in general, they're just connected differently and they don't have that same molecular formula. We already went over the fact that they have the same connectivity, so let's go ahead and put a check right there. Next, let's look at R and S, right? To determine R and S, we're going to look at the highest priority off of the chiral center. Now, before we go over R and S, a quick recap for those that don't remember, chirality essentially means you have a stereocenter or a carbon with 4 different functional groups around it, right? So an example of a molecule that would not be considered chiral would be this. All right, we don't have four different functional groups around this carbon, or four different atoms around this carbon. We clearly see we have two hydrogens and we also have two fluorines, right? To make this a chiral molecule, we would have to change one of these to maybe, let's say, a chlorine, and one of these to, let's say, maybe a propyl group, right? Propyl group. This will then make this a chiral molecule, right? So let's go back here, right? We clearly see we have four different connections around our carbons, and they're the same connections. Therefore, we have connectivity check and we have chirality check. So these are chiral molecules. Now, highest priority. You always start at the center, or at your chiral center, and then you look at the next atom coming directly off of that chiral center. So in this example, we're going to be comparing oxygen to fluorine. And remember, the ethyl group, the first thing off the ethyl group is a carbon. So we're going to be comparing oxygen to fluorine to a carbon to a hydrogen. Now, the atom with the greatest molecular weight is going to win, and then dictated as 1. Then the second highest would be 2, 3, and so on and so forth. So we know that fluorine is going to be higher than oxygen in terms of molecular weight. So this would be 1. This would be 2, 3. And your hydrogen is typically always going to be 4, right? So right off the bat, you can usually just go ahead and write 4. Now we are going to follow the numbers, right? 1, 2, and 3. And we're going to draw an arrow starting from 1, 2, 3, all the way, right? Now notice this is going clockwise, right? So when things are going clockwise, we give that an R configuration. So clockwise equals R, and S equals counterclockwise. One of the ways that I like to remember this is that R is one letter less than S. Clockwise is one letter less than counterclockwise if you put it in an abbreviated form. So that's one of the ways that I like to remember R and S, because sometimes it does get difficult to remember, is counterclockwise R or is clockwise S. Just remember, R is one letter less than S. Clockwise is one letter less than counterclockwise abbreviated, right? So this is going clockwise, therefore we say this chiral center is going into an R configuration, right? Now, notice once we get to R, remember that your hydrogen always has to be on a dash, right? If it's not on a dash, then we switch it from an R to an S. So say for instance, this was on a wedge, right? That means our least priority group is now on a wedge. If our least priority group is on a wedge, that means we have to invert the stereochemistry from R to S. But since it was originally on a dash, we don't have any inversion of stereochemistry to do. So this is going to stay as R, right? Now let's do the same thing over here. 1, 2, 3, and 4, right? This is going counterclockwise. But what do we notice? Since this is going counterclockwise, right, we are going to say that this is an S. But what do we notice? Our hydrogen, our lowest priority group, is on a wedge, which means we then have to invert our stereochemistry from S to R, right? So we're going to invert our stereochemistry from S to R because our lowest priority group is on a wedge, right? Another way of thinking about that is that one of our highest priority groups would be on a dash, which we don't want to happen, right? So this is going to go from S to R. Now what do we see? From R to, we have the same connectivity, right? The same optical activity, because this is R and this is R, and if that's the case, that means these molecules are the same. These molecules are the same because they have the same orientation and they have the same connectivity. At first glance, you wouldn't think that these molecules would be the same, but when you do the R and S, you clearly see how easy it is to see that this is an R configuration. They're connected in the same way, therefore these molecules have to be different. If, for instance, this was an S, say for instance, just for the sake of argument, that we kept this at an S, right? Then these molecules would be enantiomers. Enantiomers have opposite R and S at every chiral center. Very important to remember that. Enantiomers will have opposite R and S at every single chiral center. If you don't have an opposite R and S at every single chiral center, then you're going to be dealing with a diastereomer, right? So, in terms of symmetry, it doesn't matter here because there's only one carbon. So, symmetry really only matters due to meso compounds, right? If we have symmetry, if we get a lot of requests for videos on meso compounds, I can go more in depth on how symmetry will convert one of these molecules into a meso compound. But remember, this was originally a wedge, right? Therefore, we had to switch that from S to R. Therefore, these molecules are the same because they have the same optical activity and the same connectivity, right? So next, we're going to do another problem on diastereomers and talk about how we can differentiate between whether or not the molecules are going to be diastereomers, the same molecule, and enantiomers, or if they're going to be different compounds in general.